Hi, in this lesson, we're going to look at a spreadsheet activity. The goal of this activity is to help you link up the ideas of displacement, position, with acceleration. Since they appear in two different equations, but not in the same equation, at least with the two that we have so far. I'm going to take you through a very simple example and then a somewhat more complicated example, and then the most complicated example, which is this everything tab down here. But basically what you're going to see each time when you open these up is you're going to see a spreadsheet that looks sort of like this. It's going to have some constants, initial conditions, and then time equals 0 most likely at the starting point. After we go through these ones, you're going to try some on your own. So let me just walk you through the setup of this. It's a little bit complicated. I tried to color code things and make it as easy as possible for you to understand what I'm asking you to do. So first box up here, constants and initial conditions. The two constants that we're going to have are time interval and acceleration. In this case, we're going to do the simplest one possible, which means acceleration is going to be 0, and the time interval is 1. I'll show you the ramifications of changing that. It's not a big deal, but it does affect all of the outcomes if we change our time interval. Then we have initial conditions. Where is this thing starting, and what is its initial velocity? Then down here, I've broken up the variables that we're going to be solving for into two different categories. There's instantaneous ones, and instantaneous just means what is happening right at this instant. So what is the time right at our initial instant? Well, it's 0. What will be our time after one time interval? It'll be 1. What's the position going to be at this instant of time? What's the velocity at this instant? So these are just at one particular time that we'll be filling this stuff in for. The interval variables, change in velocity, average velocity, and change in position, also known as displacement, those things take place over an interval of time. You can't say that the change in velocity at time equals 1 second is equal to 5 meters per second. That doesn't make any sense. It has to have, in order for the change to occur, it has to occur over some finite amount of time. And if you're trying to take an average, I guess you could say that you have an average velocity at one instant of time. But normally when we're doing averages, we're taking multiple things and combining them together to see what the average value is. So these are all taking place over an interval of time. So I'm going to start filling this out, and hopefully it'll also make sense as I do that. So I could just type in, 1, 2, 3 on the way down, but I like Excel, so I'm just going to go ahead and do this. So I'm saying look at the previous column, and then with this part here, I'm saying and add to that, I shouldn't say previous column, look at the previous time, and then add to that the time interval. And I've used the money signs, the money signs, dollar signs, to lock in this cell. So it doesn't change where it's looking. It's always going to look at that cell. This one is actually always going to look one time above. So I'll show you what this looks like then. I'm going to have to copy and paste manually because I've got those little intervals in between. But we get this change in time. Position, initial condition tells me that that's 2. I could just say look up here. And for initial velocity, I'm just going to tell it to look at this too. That way, if I want to change something, if I decide, you know what, I actually want that to be 5 or I want that to be 0, I can make that change really quickly. Now we get to the part where we're starting to look at what's happening. We have to actually do some calculations. So I'm going to remind you, first of all, that there are two primary equations that we have at this point. Average acceleration equals change in velocity over change in time. As long as we're dealing with a constant acceleration, which we are, then this becomes the constant acceleration equals change in velocity over time. And average velocity equals change in position over time. So our first step here is going to be to find the change in the velocity. And that's really easy to do in this case because change in velocity from this equation up here is just acceleration times time. Our acceleration is 0. So our change in velocity is just going to be 0 every single time. And I could do that formulaically, but I don't have to. It's just 0. So that's the first step. The second step, now that I know what the change in velocity is I can find the velocity at the end of each of these 1 second time intervals. So I'm going to go over here then, and all that I'm going to do is I'm going to say, well, let's look at the previous value of velocity, in this equation over here, that's v1. Let's add to that the change in velocity that occurred during that interval of time, and that will give me my new velocity. And I can do that for each of these, and not surprisingly, because there is no acceleration, the velocity is the same the whole time. So this is actually a really non-illustrative example, but it's so basic that hopefully things make sense, and we can get into more confusing stuff in the next spreadsheet. So average velocity then, well, if I know what the initial velocity is for each time interval, and I know what the final velocity is for each time interval, then I should be able to take an average because I've passed 5th grade math. And that just means add up the two numbers, divide by 2. So that's how we're going to get the average. Average, just take these two, add them up, and divide by 2 since there's 2 of them. And again, I'm just going to copy and paste that down. And we see that our average velocity is just 3, which is not surprising because it starts at 3, it ends at 3, it's 3. Now we know what the average velocity is, we can find the displacement. So in order to find the displacement, what we're going to do is we're just going to take that average velocity and multiply by the time interval that we have. That'll tell us not where we end up, but how far we went during that interval. So again, all I'm doing is I'm taking the average velocity, I'm multiplying it by the time interval, which I gotta go up here to get, and I want that locked in because I'm just gonna use the same time interval the whole time. And I'm just gonna copy and paste that down. And not surprisingly, we move 3 meters in every 1 second time interval. If you're moving at 3 meters per second on average, for 1 second, you're gonna move 3 meters. That is not where we ended up. We haven't quite gotten there yet. We still have this position column to fill in. And that will be our last one. So to find the new position, we're just gonna say it's equal to our old position plus how much we changed it by. So, old position plus how much changed during that interval of time. And I can then just copy and paste that down. And we see that we've increased our position by 3 meters for every interval of time. And that's it. That's all that we have to do. Okay, now I could change things up a little bit here. I could say, well, what if this was a 2 second time interval? Well, the nice thing about doing this with equations is that everything that needs to change changes, right? So 3 meters per second for 2 seconds means 6 meters. And so if I start at position 2 and change my position by 6, I end up with 8. If I change it by 6 more, 14, etc. And if I really want to, because I'm in Excel, I can go up here and I can just graph things. Right, so I can graph this and I can see that there's this trend and it's linear. Okay, so the position versus time is linear, it's a straight line. Not surprising. We would expect to move the same distance for every interval of time since we're not accelerating. All right, so that's the most basic case. All right, so now we're gonna do a different situation where we have an object, it starts at a position of 0, with 0 initial velocity, but it does now have an acceleration. So a lot of the stuff that we did doesn't really need to change. I'm going to start off with zeros here though, and I'm going to go through this in the exact same order that I went before. Nothing has changed. I know my acceleration now, it's not 0. So the first thing I'm going to do is find what is this change in the velocity that occurs. Well, the change in velocity is just the acceleration times the time interval. So I'm going to go ahead and I'm going to multiply that by that. And these are constants, so I want to make sure I lock them in. No, yeah, okay. I don't know what just happened there. Does that look like a B2? There we go, okay. So I've got my change in velocity. In a 1 second interval, if I change my velocity by 2 meters per second each second, I'm going to change my velocity by 2 meters per second during that time interval. And that's going to be true for every 1 second time interval. Right? This is the nice thing about a constant acceleration, is that the change in velocity for every constant length time interval is going to be the same. Now that I know how much the velocity is changing by, I can go over here and I can find out what the new velocity is after each interval of time. So if we start off with a velocity of 0, change it by 2, we would probably expect to get 2. If we then change it by 2 more, we would expect to get, hopefully you said 4. So I'm going to just go ahead and actually type in the formula here, if I can get this to work. So I'm just going to say my new velocity is the old velocity plus the change in velocity. Pretty easy. Okay, so it just goes up by 2 each time. Now what I can do is I can go ahead and find out what the average is. Well, if we're starting with 0 and we end up with 2, the average of 0 and 2 is 1. If we start the next time interval at 1 second with 2 meters per second, and we finish that time interval at 4 meters per second, we went from 2 to 4 meters per second, that's an average of 3. So again, I can write that out if I want to, or I can just type it in and do the calculations for me. So the initial and the final of the interval divided by 2. And I can just drag that down. And we see, not surprisingly, that pattern where the average velocity is increasing by 2 as well, but it's situated at the halfway. So halfway between 2 and 4 is 3, halfway between 4 and 6 is 5. Now that I found the average velocity, I can go ahead and I can find how far we've moved in these intervals of time. Well, because the time interval in this case is just 1, I don't really need to do this, but just in case I decide that I want to change the time interval, seems like this is the way to go. Okay, so if I go at 1 meter per second for 1 second, I'm going to go 1 meter. 3 meters per second for 1 second, going to go 3 meters during that interval of time. Again, this is not where we ended up. This is just how far we went in that interval of time. To find out where we ended up, we have to know where we started. So where did we start? Plus how much did we change our motion by, or position by? So if we start off at 0 and we moved by 1, we're going to end up at 1. If we start at 1 and we change our position by 3, we're going to end up at 4. And then if we change it by 5, we're going to end up at 9. And if we change that by 7, we're going to end up at 16. And if we change 16 by 9, we end up at 25. So hopefully what you can see here is a little bit of a pattern. 0, 1, 4, 9, 16, 25. Those things all have something in common. And hopefully as you're looking at it, you're realizing that what they have in common is squareds, right? And if I look at this, 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, 5, 25, these in fact are just the time squared, right? And I can graph this and you'll see a beautiful little parabola. Okay, so I've got a parabola here. I can even fit an equation to this. Polynomial. Let's put the equation on the chart. Don't worry about these 10 to the negative 15ths. Those are awfully small. So this ends up saying that the position is equal to the time squared. So we have a little bit of a relationship here, which is that x of t equals t squared, which is pretty cool. In our previous one, we didn't really come up with a general equation for this, but x of t was just equal to v initial times t, right? There was nothing super fancy about it. We just, actually plus, there was a plus here. So we had the initial position plus all of that, okay? And you can go back and look at that if you're not 100% convinced. We started at position 2, and then we added, we just changed the time interval to 1 here. And we added 3 each time, right? And that's because of the v naught times t. Here we had no initial position, no initial velocity. And so the only thing that mattered here was actually the acceleration. We're going to deal with this on your own. You're going to try to figure this out on your own. And also it'll be the topic of a future video. So let's take a look at the final example here. The final example is the same, except different initial conditions. So now I'm putting everything in here. We have an initial position of 2, initial velocity of 3, and an acceleration of 2. So we can just plug those in, right? So here's the initial position. Here's the initial velocity. And then we're going to have to calculate what the change in velocity is, just like we would have before. Okay, so after doing that, we can see that we've got a change in velocity of 2 meters per second every second. Not surprising, our acceleration says exactly that. Then we're going to go ahead, and if we found what the change in velocity is, we can find what the final velocity is by just taking the initial plus the change in velocity. All right, and you see that it goes up by 2 every time. Not surprising because we're changing our velocity by 2 every time. Once we know the initial and the final, we can find our average by taking the initial and final values of any given time interval. All right, and so we can see that our average is still going to always be halfway in between the initial and final value for any interval of time. And once we know our average velocity, we can find the displacement. Because we're using a time interval of 1, the displacement has the same value as the average velocity. If you go 8 meters per second for 1 second, you're going to travel 8 more meters compared to wherever you were already. So the last step is the one where sometimes people get mixed up. This is the one where we're making our final leap to find out where something is based on all of its initial conditions and whatever acceleration it has. And for that one, we just say that we're going to look at our previous position and add to our previous position the displacement, how far we've moved. Okay, so what I'm going to leave it to you to try to do is figure out what the equation is that describes the position related to velocity, initial, position, initial, and the acceleration. And then I'm going to give you some other ones to work on and ask you to turn some of that stuff in. So this is the basic approach. It's a very labor-intensive approach. You're going to find an easier way to do all of this. But this is a good way to start off seeing the connection between all of these different pieces, how they influence each other, and how you can go from some initial conditions to final positions.